Today we have problem B2 from the 2025 Putnam, where we're given a function f from the closed interval 0 to 1 to 0 to infinity, and it's strictly increasing and continuous. So sort of drawing that out, we have f looks something like something like this, right? Just any continuous function that's strictly increasing uh, on 0 to 1. When we let R be the region bounded by x is equal to 0, x is equal to 1, y is equal to 0, and y is equal to f. So that is just this region inside here, right? When we let x1 be the x-coordinate of the centroid of R. And so if you recall, centroid is pretty similar to center of mass, where it's the point where if you balance it, then it will balance perfectly there, right? And I guess the difference between those two is centroid only cares about the geometry of the object, where center of mass will, if it's like a physical object, it'll take into account of the material as well, since different material weigh different things. But for centroid, we only care about the geometry. So for this shape, our centroid will be somewhere like here. And then we let x2 be the x-coordinate of the centroid of the solid we get by rotating r around the x-axis. So I can try to draw that out, but it'll probably look quite bad. Um, 0 to 1. From, we have f above the line. When we rotate it, it'll be below the line. And then because we rotate it around r, we'll rotate it around the x-axis. We'll have these sort of circles like things at each point of x. And then on the other side, it looks something like that. So I guess if you can imagine, like, this sort of looks like a cut of fish, where it's a circle around the entire x-axis based on f. And I guess we have x2 somewhere like here. And we want to prove that x1 is less than x2. And so to do that, it'd be nice to have a formula for both of them. And if you've taken a Calculus 3 or multivariable calculus or physics course, you might remember that the centroid is a weighted average of the shape we're looking at. Right, so in particular for x1, we have that x1 is the integral from 0 to 1 of each position times its sort of weight, or f of x, because that's its height with respect to x. And then to make it a weighted average, we divide by the total area. And similarly for x2, we have that x2 is the weighted average of our solid here, where again we have the integral from 0 to 1 of x, but this time at each x position, our weight is the sort of circular disk that we sort of generated by rotating r around the x-axis. And in particular, that circular disk will have a radius of f of x. So our weight will be pi f of x squared all over the total volume this time. So that's for each x, we sum over each circular plate, or pi of f of x. Pi times f of x squared. And so we can immediately cancel out the pi's to just have x2 is the integral from 0 to 1 of x times f of x, or x times f of x squared all over the integral from 0 to 1 of f of x squared dx. And so now we wish to prove that x1 is less than x2, or that, I'll just copy these over. X1 here is less than x2 here. And just to get rid of the fractions, we can cross multiply to get integral 0 to 1, or I guess just rearranging completely, we'll get that we want 0 is less than the integral of 0 to 1 of x times f of x squared dx times the integral of 0 to 1 of f of x dx minus the integral of 0 to 1 of x f of x dx times the integral of 0 to 1 of f of x squared dx. And so I guess for both of these sort of integrals multiplied by each other, they're both from 0 to 1. So if we can, I guess, try to write them as a double integral instead, then we can combine all of it into a single double integral, and then we can see where we go from there. And I guess for the sake of rigorousness, there is this theorem called Fubini's theorem that allows us to combine each product of integrals into a double integral. And the condition for that is that we need the functions inside to be completely continuous on the area that we're looking at. And in this case, it's from 0, it's sort of a square area of 0 to 1. And because f of x is continuous, we're able to do this, or Fubini's theorem allows us to combine it. And so we can combine it in this way. The area we're looking at from 0 to 1 of x and y, we can make this first term with respect to x, and the second term with respect to y. And similarly for the other one, it's over the same area of f of x times f of x times f of y squared dy dx. And so combining them and factoring, we have that 0 is less than x times f of x times f of y times f of x minus f of y dy dx. And so this is what we want to show now. And we see our expression inside is very close to being symmetric. Right? We have an f of x, f of y, we have an f of x minus f of y, but we sort of have this lonely x here. So I guess we want to find some way to get a minus y into this equation now. And we can by, I guess when we got from here to here, we made this first term x and the second term y for both of them. But if we make the first term y and the second term x, we sort of get what we're exactly looking for. So instead we'll have that the integral from, or the double integral from 0 to 1 of y times f of y squared times f of x dy dx minus, again, the double integral of y f of y times f of x squared dy dx. And so now combining and factoring, we'll have the double integral 0 to 1 of y f of x f of y minus f of x. Right, and so just switching the order of this will give us what we want. Right, and so now if we add both of these two equations, we'll immediately have the double integral from 0 to 1 of x minus y f of x f of y, right now f of x minus f of y dy dx. So now we have this sort of nicer looking equation that we want to prove is positive. And from the conditions that were given, again, if we look back at f is strictly increasing and it's mapped to the non-negatives. So in particular, that means f of x is greater than 0, is greater than or equal to 0, f of y is greater than or equal to 0, and then we can't really make x minus y always greater than or equal to 0, or f of x minus f of y always greater than or equal to 0, but we can look at their product instead, right? We can consider them as one unit. And so and we can make use of the fact that f is strictly increasing. So when x is greater than y, we have f of x is greater than f of y. That's what strictly increasing means. So we have that expression is going to be positive. And when x is less than y, I guess I'll write it out. We have x minus y is greater than 0. F of x minus f of y is greater than 0. So x minus y times f of x times f of x minus f of y is greater than 0. If x is less than y, then x minus y is less than 0. Again, because it's increasing, we have that f of x minus f of y is also less than 0. So we again have that the product is going to be greater than 0. With equality, I guess the case for x is equal to y, we just have x minus y is equal to 0. So we have that the product is equal to 0, but that's not negative, so that's okay. So we have that over the entire area that we're integrating over. Our sort of expression inside is always non-negative, and it's at least positive somewhere, right? So that necessarily means that we indeed have this to be true, right? The integral, the double integral over our expression holds. And so because this holds, we're done. Because we can just go backwards, we eventually get that, right? X1 is less than or equal, x1 is less than x2.